what is the derivative of f of x equals ax to the power n at point x comma y? Hi there. Well, in the last lesson we were wondering if we could find a derivative for any polynomial, because that would be really powerful. And let's see if we can use the same technique that we used to find the derivative of 3x cubed. Okay, so what we said was, I'm not sure if I used the y equals or the f of x equals. I'm going to use the f of x equals because I've got f of x up here. So what we're looking for is the limit as delta x approaches 0. In fact, I should say what it is I'm looking for. The derivative of f of x, which is f prime of x, is equal to the limit as delta x approaches 0 of, and it's delta, that's capital delta this time, f of x over delta x, which is equal to f of x plus delta x. That's the little bit bigger bit minus the original bit, and that's the change in f of x divided by the change in x. Well, that's going to be x plus a little tiny bit of x minus x. And of course we've got the x there, we've got the minus x there, so they just cancel out. So this is our formula for our finding our derivative. It's the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. And I apologise, I'm using two lots of deltas here, so we've got a capital delta and our lowercase delta. Right, so let's expand this out. So we've got this lot here, on our left hand side, and I'm going to move this down under the limit to make it easier to give myself more space to write with. And that is equal to, so f of x plus delta x, we've defined f of x as equal to ax to the power n. So this is a times x plus delta x raised to the power n minus ax to the power n, and that's, oh, that n is terrible, isn't it? So that's, there we go, that's n, and then that's all divided by delta x. What do we want now? Right, we need to expand out x plus delta x to the power n. That is going to be tricky. Okay. Right, I'm going to want some more space. And I'm going to put a line down here so we've got some space, so we know that this is something different. Okay. Okay, so we'll recall that anything raised to the power 0 is 1. So let's just write a plus b raised to the power 0 is equal to 1. And we know that a plus b raised to the power 1 is just a plus b. But we can also write a plus b as 1 times a to the power 1 plus 1 times b to the power 1, and you'll see why in a minute. Okay, so a plus b to the power 2, or a plus b squared, we'll recall is a squared plus 2ab plus b squared. Now I want you to note something. This term is 2, or the power is 2, and the middle term here is a 2. Also, the very left term is raised to the power 2. Okay, and if we recall from the last lesson, we actually multiplied it out longhand, but we concluded that a plus b to the power 3 is equal to a cubed plus 3a squared b plus 3ab squared plus b cubed. And I actually just want to write the ones in again. So there's a 1 there and a 1 there. And there's a 1 here and there's a 1 here. Okay, so we'll note again that a plus b cubed is raised to the power 3, and the first a term is raised to the power 3, and then the next term, the second term, has a coefficient of 3, and the final term is just 1 times the second term, the b, raised to the power of 3. Now this pattern is something called Pascal's triangle, and let me just explain how to do Pascal's triangle. If we start with a 1, and then we write the 1 and the 1 either side of that 1, and now we write a 1 to the left of that 1, and then we add that 1 to the 1 immediately above it, and that makes a 2. Actually, what we do is we add these two 1s, sorry, and that makes a 2, and then we have our final 1. And now we extend the pattern, so we have a 1, and 1 plus 2 is 3, and 2 plus 1 is 3, and then we have our 1 at the end. So that's our a plus b to the power 3. And then for the fourth one, we can do the same thing again. We put the 1 down, and then 1 plus 3 is 4, 3 plus 3 is 6, and 3 plus 1 is 4, and then we have our 1. And so that would be the coefficients of a plus b to the power 4. So we could write a plus b to the power 4 is equal to, so that's 1 times a to the power 4 plus 4 times a cubed. Now you'll note that the a's index goes down by 1 each time, and the b's index goes up by 1, so that could be considered b to the power 0, and now this is b to the power 1, and then plus 6 times a squared b squared plus 4 times a b to the power 3 plus 1 times b to the power 4. So there's our pattern. So a plus b to the power 5, then that would be a 1 and then a 5 and then a 10 and then another 10 and then a 5 and then a 1, and then we would follow the same pattern. But again, notice that this is raised to the power 4 and this coefficient here is a 4, and the a terms go down by 1 each time and the b terms go up, or the index of the b terms goes up by 1 each time. So if we extend this to a plus b to the power n, what we will get is equal to 1 times a to the power n plus, and this is the index, so the index is n, so this is n times a to the power n minus 1 times b plus a whole lot of stuff that we won't even look at. That's just a large number of other terms, with a constantly going down by a power and b going up a power, and we don't care what the middle bits are, plus 1 times b to the power n, which is how it will end. So this is our expanded form of a plus b to the power n. Now again, I'm going to substitute, where I see a, I'm going to substitute x, and where I see b, I'm going to substitute delta x. So we have, I'm actually going to zoom in just a little bit to make it easier to write. So we have a multiplied by, so we've got x to the power n plus n times x to the power n minus 1, and then the b would make it delta x plus, and then there's I can't think of the word. Oh my goodness, I can't think of the word. Indefinite. I kept wanting to say infinite, and I didn't want to say infinite. I want to say indefinite. An indefinite number of terms, depending on how big n is. And then it's all going to end with b, not b, because b is delta x. So this is delta x to the power n, and that's all. We've got to subtract that a times x to the power n, and then all that is divided by delta x, and I think that's the hardest part done. Okay, so all of this is equal to, and what I want to do now is expand out these brackets by multiplying every term in the brackets by a. So this is a x to the power n plus a n x to the power n minus 1 times delta x plus, and an awful lot of terms. And the thing to remember is these indefinite number of terms that's symbolised by the ellipses here, they're all going to have increasing powers of delta x multiplied by them. And the reason I don't care is because they're going to disappear when we find the limit. And just like this last term here is going to disappear. No, that should be a. So this is a times delta x to the power n, and then we're subtracting all that from ax to the power n, and then this is all divided by delta x. And again, look, we've got ax to the power n here, and we've got negative ax to the power n, and that if you add ax to the power n to negative ax to the power n, or if you subtract ax to the power n from ax to the power n, you're going to end up with 0, and 0 plus anything is whatever you had to begin with. So these two terms cancel out. And now we can cancel out the delta x, because we know delta x is not 0, but it's very, very, very close to 0, and that should be delta x to the power n. So that's going to be delta x to the power n minus 1 there. Okay, and so we now have, just want to tidy this up a little bit. This is equal to a n x to the power n minus 1 plus, now we've got a load of dots, and we've got a times delta x raised to the power n minus 1. Okay, so all these terms here with the dots have got delta x raised to some power, and as we find the limit as delta x approaches 0, all of those delta x terms are going to get closer and closer and closer and closer to 0, to the point where they're so small we can completely ignore them. So when we solve for the limit, we're just going to end up with the derivative f prime of x is equal to a n x to the power n minus 1, because all the other terms get progressively closer to 0, to the point where we don't care about them anymore. In fact, the limit, they will be 0. We will treat them as 0 in order to get the limit. And that is our derivative of any polynomial in the form of a n x to the power n minus 1. Now, we're not quite there yet. There's a couple of other points I need to deal with before we can find any polynomial. And these two concepts are that the sum of limits is equal to the limit of the sum. So put that symbolically, the limit as x approaches some number, let's call it a, of f of x plus g of x is equal to the limit as x approaches a of f of x plus the limit as x approaches a of g of x, and vice versa. Either way will work. And what falls naturally from this rule, or the addition rule of limits, is the addition rule of derivatives, So that means that the derivative of f of x plus g of x with respect to x, I'm mixing both terms now, which we can do, is equal to the derivative of f of x by dx, which we know is also f prime of x, plus the derivative of g of x by dx, which of course is equal to f prime of x plus g prime of x. Okay, what does all that mean in practice? Well, in practice it means if you have some polynomial in the form of ax to the power n plus bx to the power m plus cx to the power l whatever plus dx to the power q, or so anything like that. In order to find the derivative of all of that, you can just find the derivative of each term individually and add them up. Let's put that into practice really quickly and work through an example. And I'm running out of space. Let's choose 2x squared plus 5x plus 1. And that's all equal to y. And we want to find dy by dx. So all we do is find the derivative of 2x squared. So now we know that the derivative is anx to the power n minus 1. So what we do, we take the power and we multiply that by the coefficient, and then we reduce the power by 1. So that 2 is multiplied by the 2 to make 4, and then we write down the x, and that 2 becomes a 1, so that's 4x to the power 1, and 4x to the power 1 is just 4x, and then we add. Now we've got 5x. What do we do with the 5x? Well, we remember that 5x is the same as 5x to the power 1, and 1 times 5 is 5, and then we reduce the power by 1, so x to the power 1 becomes x to the power 0, and anything to the power 0 is 1, provided x is not equal to 0, but even then we would find the limit, and so this will just be 1, and 1 times 5 is 1. So we've got 4x plus 5, and then the constant term has no x, so this is 1 times x to the power 0, and 0 times 1 is 0, and anything multiplied by 0 is 0, so we would be adding 0, so we don't need to add anything. So the derivative is just 4x plus 5. Okay, I think that should do it for derivatives. I think I'll pick up from here in the next lesson. It never ceases to amaze me though just how much hard work we had to do to find such a beautifully simple method for finding the slope of a curve at any given point. Okay, so I will leave you with a quick question and then we'll pick up in the next lesson.